But what I'm going to do is to say a bit about my own subject, astronomy, and then the limits of science more generally. Of course, we heard about Galileo, and of course, in recent years, we've had pictures of all the planets taken close up by spacecraft. I'll give you a quick tour. If you go out from the Earth, you hit the red planet, Mars, and this object, Curiosity, was landed 4 years ago on the surface of Mars, and it's been crawling around that surface. You can't see very well, but these are the tracks that it made, and it's traveled about 30 miles doing geological observations, sending back pictures like that and like that of the surface of Mars. Probes have been out to Jupiter, looking at its 4 moons, again discovered by Galileo, and they're very different. Europa has an icy surface, and Io is a really sulfurous place, like the Earth 2 billion years ago. Going further out, here's Saturn. Saturn's got moons too. This is Enceladus, a small moon which is covered in ice, and we know there's an ocean underneath it. And this, on the other hand, is Titan, the giant moon, and this is this has these lakes on it, but it may look a rather nice place, but the temperature's minus 106 degrees centigrade, and these lakes are liquid methane, so not a good place to live. In the last year, the European Space Agency sent a probe to a comet, and this little robot here actually landed on the comet, and we also had pictures sent back from Pluto here by an American spacecraft. And what's amazing is that Pluto is 10,000 times further away than the moon. It sent back these pictures, and of course it's using 1990s technology, because it was 5 years planning the thing, 10 years to get there. And so you can think how much better one could do with these robots if one was doing it now. Now, everyone wants to know, is there any life on any of those places? There might be something swimming under the ice of Enceladus. There's probably nothing much on Mars, but things are much more exciting if we look beyond our solar system to the realm of the stars, far further than we can send any probe today. One of the most exciting discoveries in recent years has been that most of the stars in the sky are orbited by retinues of planets, just like the Sun is orbited by the Earth and the familiar planets. These planets aren't seen directly, they're seen by transits. If you look at a star, and if a planet moves across in front of it, it blocks out a bit of its light, so the brightness of the star dips every time. So if you see regular dips, you know a planet is coming round. And a spacecraft called Kepler looked at an area of sky for several years, monitoring the brightness of stars very precisely, and it found thousands of planets. They're depicted in this rather silly picture, which shows to scale the masses and the orbital periods, the years on these planets. The special interest attached to planets like the Earth, of course, the same size as the Earth and the distance from their stars such that water can exist. We can't directly see these planets yet. We need bigger telescopes than we've got now, but we will have them. This is a design for a telescope already being built by the Europeans. They're not very imaginative in their nomenclature. It's called the Extremely Large Telescope. And it will have a mirror, or mosaic mirror, 39 meters across. This room is about 10 meters wide, so think of a mirror about 4 times as big as the width of this room. And this will be able to image planets like the Earth orbiting nearby stars, and learning spectroscopically something about their atmosphere, whether they've got oceans, whether they are green, etc. And that'll be really, really exciting. And so the question, though, is, even if you have an environment like the Earth, how likely is it that we will have life on it? As I said, most stars have planets around them, and 1 in 6, we think, has a planet rather like the Earth. How likely is it that life gets started? We know about evolution, but we still don't really know how life started even on the Earth. what triggered the transition from complex chemistry to the first replicating, metabolizing system. Was this something that would happen in any Earth-like planet, or was it somehow a fluke here? We don't know. So there are about 1 billion Earth-like planets in our Milky Way galaxy. This is the assemblage of stars of which we're a part. But let's now widen our horizons to the larger universe, which we can now observe. This is what our galaxy would look like if we could get 2 million light years away. This is Andromeda, a disk galaxy viewed obliquely with all the stars orbiting around a central hub, where there's incidentally a black hole. Here's another galaxy viewed edge on. And we can see with our telescopes literally billions of galaxies. This amazing picture, taken with a big telescope, shows a patch of sky just a few minutes across. It would take 100 patches like it to cover the full moon, but in this region of sky there are hundreds of smudges, each a galaxy, many fully like our own galaxy, looking so small and faint because they are very distant. They're newly formed, they're about 10 or 12 billion light years away. Now, we'd like to understand a bit more about galaxies, and of course, if we are particle physicists, we would crash together particles in the lab, but we can't do that with galaxies, but we can in the virtual world of our computer. This is a simulation showing 2 galaxies crashing together and merging, a real sort of train wreck there. And I should warn you that in 4 billion years, the Andromeda galaxy is going to crash into our Milky Way, doing just like that. We have inferred by looking at distant galaxies and by other observations of radiation, etc., that our universe started off in a hot, dense state 13.8 billion years ago. That number is known to 1% accuracy. But we'd like to go back further still, because to answer the questions, why is the universe expanding the way it is, and why does it contain atoms and radiation, we need to go back much further. And I put in a hazard sign here, because there we don't understand the physics so well, because it's beyond the range where we can check experimentally. But we're working on it. I'd like to say that there is one idea, which is that our Big Bang, if we understood it properly, would prove to be not the only one, maybe just part of some vast multiverse. This is an exciting idea which is favored by many theorists, and it's speculative, but in 50 years' time, I would hope that we will have been able to firm up the evidence for a multiverse, just as 50 years ago we didn't know there was a Big Bang. Now we can talk seriously about it back to a nanosecond and say things about still earlier. This is my favorite pedagogical slide. I think this is very interesting because there are lots of links between the microworld on the left and the cosmos on the right. The everyday world of people and mountains is determined by atoms and molecules, how they stick together. Stars there are fueled by the nuclei within the atoms. There's a link there, and there are other links. On the left-hand side, the microworld, the dominant physics is quantum theory. On the right-hand side, Einstein's theory holds sway. Now, general relativity and quantum theory are the 2 twin pillars of 20th century physics. But, as you probably know, they haven't yet been meshed together. Unfinished business is a unified theory. Now, in most contexts, this doesn't matter. But if we really want to understand the beginning of the universe, not just the first nanosecond, but the first tiny, tiny fraction of a second where the conditions were imprinted, we've got to achieve the synthesis symbolized as well gastronomically at the top of this picture between quantum theory and gravity. Because right at the beginning, the whole universe was squeezed to microscopic size. So quantum fluctuations can shake the cosmos. And in order to have a theory that can understand that, we need to have this unification, which still eludes us and is really still unfinished business. And it may tell us whether there is this multiverse. And that would be a surprise, but it would be a further Copernican demotion, as it were. Our solar system is one of billions of planets and planetary systems in our galaxy. Our galaxy is one of billions of galaxies accessible to our telescopes. but this entire panorama may be the aftermath of one big bang among billions. That is speculative science, but it's an exciting prospect that widens our horizons in an almost mind-blowing way. So there are these two frontiers of physics, the very small on the left, the very large on the right. But 99% of scientists work neither here nor here. They work on the third frontier, the very complex, insects, people, and mountains. Things large enough to have layer upon layer of intricate structure, but not so large that they're crushed by our planet's gravity. And that's the biggest challenge. The smallest insect is more complex than a star or a galaxy. And that's why it's actually not surprising that though we understand stars and galaxies quite well, our grasp of some familiar matters of interest to us all, diet and childcare, for instance, is still so meager that expert advice changes from year to year. It's ironic that you shouldn't believe anyone on those subjects, whereas I hope you half believe me when I talk about stars and galaxies. The sciences are sometimes likened to a hierarchy. Different levels of a tall building. Maths and particle physics at the bottom, then the rest of physics, then chemistry, then cell biology and so on, up to psychology, and then the economists in the penthouse. And there's a corresponding hierarchy of complexity. Atoms, molecules, cells, organisms, societies, and so forth. But the point I want to make is that the analogy with a building is poor. In a building, insecure foundations imperil the rest. But the higher-level sciences dealing with complex systems aren't imperiled by an insecure base. Each science has its own distinct concepts and explanations. For instance, mathematicians trying to understand why flows go turbulent or why waves break don't care that water is H2O. They treat the fluid as a continuum. And everything, however complicated, breaking waves, migrating birds, tropical forests, is made of atoms, and it obeys the basic equations of quantum physics. But even if those equations could be solved for immense aggregates of atoms, they wouldn't offer the enlightenment that the scientists seek. Reductionism is true in a sense, but not in any useful sense. Each science has its autonomous concepts and laws. Each is equally fundamental. As I said, biologists aren't held up by uncertainty in subnuclear physics. And that's important for us to realize at this meeting when we are addressing the whole range of science. Another question, is science an unending quest, or will we perhaps, somewhere far down the line, hit the buffers? This could happen for two reasons. Obviously, some topics get cleaned up and codified, atomic physics, for instance, and researchers then move on. But maybe we should be open-minded about the obverse possibility that we hit the buffers because our brains don't have enough conceptual grasp. Einstein averred that the most incomprehensible thing about the universe is that it is comprehensible. He was right to be astonished because our minds haven't changed much since our ancestors roamed the African savanna, and it's amazing that these minds can comprehend so much of the counterintuitive world of atoms and the cosmos. Nonetheless, and here I'm sticking my neck out a bit, maybe some aspects of reality are intrinsically beyond us, in that their comprehension would require some post-human intellect, just as quantum theory is beyond the brain power of monkeys. This links, of course, to computers and AI, and it may be that in some sense the computers will understand and be able to make predictions, but that still doesn't mean that we will be able to grasp these complications. So we will hit the limits of what humans can actually really grasp, even if perhaps there are no limits in principle to what we can compute. And following on from what Terry said, experts disagree on how long it will take before machines achieve general-purpose human-level intelligence. Some say 25 years, others say never, and the best average in a recent survey was about 50 years. But some do claim that once a threshold is crossed, there will be an intelligence explosion. That's because electronics is 1 million times faster than the transmission of signals in the brain, and because computers can network and exchange information much faster than we can by speaking. And they will perhaps eventually be what makes the great discoveries, discoveries whose reasoning we will perhaps never understand. These thoughts, incidentally, lead me to believe that if we ever detect artificial signals from intelligent life in space, and although simple life may be common, intelligent life may be rare, then that signal may come from machines, not from any kind of organic civilization. No one's holding their breath for that, but I am actually involved in some of these searches bankrolled by a Russian billionaire to improve the chance of detecting any artificial signals out there. Well, these predictions about AI are exciting, but they're rather scary. So also are some of the predictions about the use of biotech, advancing equally fast. In fact, 12 years ago, I wrote a book on these themes, which I called Our Final Century, ? My publishers cut out the question mark, and the American publishers changed the title to Our Final Hour. Americans like instant gratification, right? Yes. And the book addresses two concerns. First, worries about humanity's ever heavier footprints on the biosphere, but also about the risks for empowerment of individuals and small groups by these powerful technologies. So I think we do need to worry, because as they put it, spaceship Earth is hurtling through the void, its passengers are anxious and fractious, their life support systems vulnerable to disruptions and breakdowns. There's too little planning, too little horizon scanning, too little awareness of long-term risks. We'll have a bumpy ride through this century, but we should remain upbeat. We should not put the brakes on progress. We should perhaps redirect it and realize that the precautionary principle has a manifest downside. We need more technology, but guided by social science and ethics. So I give the final word to a great scientist who Sydney knew, but I was sadly too young to know, the great immunologist Peter Medawar. I quote, "The bells that toll for mankind are like the bells of alpine cattle. They're attached to our own neck, and it must be our fault if they don't make a tuneful and melodious sound." Thank you.